Hi, everybody. I'm Charlie Catrice. I'm here at the University of Toronto working on a ventilator design challenge. Now, this is not a ventilator. I would not hook myself up to it, and you shouldn't either. But it's a prototype. It's a design. It's a swing at what you could do with a few simple parts to make something like a ventilator, and potentially one day to make a ventilator. This machine was, of course, this design challenge was brought on by the COVID-19 pandemic, where we have a massive shortage of personal protective equipment along with hospital supplies and machines like this, ventilators, life-saving support, not only in our own country, but around the world. So this machine is something that could be built by just about anybody using parts that are available at a local hardware store. And that was the kind of idea. Could we make something that was simple to make, used simple tools, was built inexpensively, and could be, greatly improved upon, I'm sure, by many of the tradespeople out there who know a hell of a lot more about plumbing and electrical than I do. So my first take is this. We have a cistern at the top. The cistern fills with water, and that provides gravity-powered pressure to our cylinders, and those cylinders then provide pressurized air to the lung. So the pressure of water due to gravity on these cylinders is what's actually driving the in-breath. This machine gets hooked up to a garden hose, so it needs a water supply, and it needs a small electrical supply. Something like a 12-volt power supply, a 12-volt battery, car battery, that kind of thing would do just fine. What we have here is essentially two cylinders that are controlling the inhale and the exhale of the body. On the left, we have only fresh air in this cylinder. On the right, we have only stale air, air that has been breathed out by the body. On the left, the water levels in both cylinders rise and fall together. They're controlled by the series of valves. We have green valves, which are water flowing into the cylinders, and we have blue valves, which are open when water is flowing out through the drain. When water flows in, the water level rises in both cylinders, and on the left, that forces air through this tube and into the artificial lung, our vinyl glove for today. On the right-hand side, when water level rises, that green arrow is flowing air up vertically and through our filter into the room. So the exhale of a person is being taken into the right cylinder and then put into the room through a filter. The filter is also being used to filter air that comes in on the in-breath, and that way the person is protected from particles in the air in the room, and everyone in the room is protected from particles from the person, or water droplets, or virus-carrying water droplets from the exhale of the person. The pressure that is provided by the height of water of that cistern above this cylinder is the pressure of ventilation. You see, ventilation requires a certain amount of pressure to inflate the lungs, and that pressure happens to be about 40 to 50 centimeters of water. That's a measure of pressure that has to do with the height of a column of water above a surface. So simply by making this thing out of water, that is a natural kind of way of providing that pressure. And this cistern can be moved up and down on a rail behind here to change the pressure provided to the lungs. Okay, so I told you what happens when the water level increases. What happens when the water level decreases? When it decreases, because that would be the blue valves are all open, so the drain of water is coming out, and we have air flowing in from the filter up here, filling the fresh cylinder. That's going to get loaded up for the next inhale breath. Meanwhile, the person is exhaling. The blue line carries air out into the stale cylinder, where we have that cylinder being filled with air, and so that on the next breath, the air can be expelled through the filter. Okay, so let's see it in action. We've got our 12-volt power supply here. We've got a couple of switches that are controlling the series of valves. The green switch on the top is going to be controlling the in-breath, so the glove will inflate. The blue switch, the exhale. Our cistern is filled with water and has a switch on it to keep it filling as water gets drained out of the system. So we turn it on, and the glove inhales, and we turn this drain on, and the glove exhales. And we're able to turn it on and off to create inhaling and exhaling of the glove and control the breath of the body. Now, this system is a little bit slow. It's slow because the diameter of these pipes is restricting flow. So at 1.25 inner diameter, these actually aren't enough. We need a larger diameter plumbing system to increase the flow rates. Additionally, some of these solenoid valves are actually restricting flow a little much. So we need a higher flow, lower pressure solenoid valve. These valves are regulated to over maybe 80 psi. That's way too much. That's almost a few hundred times more pressure than we're actually providing to them in this system. So we need a more low pressure valve system to improve the design, and we need to expand the inner diameter of the plumbing system. Our cylinders, additionally, could be fitted with encoders to measure the volume changes. And at the Y here, we should also be measuring the flow rate to know how much air is actually coming into the body and going out from the body. Okay, one last thing. When the breath comes out of the body, there needs to be a resistive pressure of about 20 centimeters of water, positive expiratory pressure. That means that prevents the alveoli and small pockets within the lungs from collapsing under vacuum pressure. We need to keep them open and use the elastic energy of the lungs to force air out into the room. And the way that we can do that, at the moment, I've got my drain below the water level in the cylinders. But if you simply move the drain up to being above the water level in the cylinders, now water has to travel up and over to leave the system. And that means that these cylinders are now actually under pressure from the water height in the tube. This allows you to easily create a smooth transition of the expiratory pressure to the lung, and also provide a variable pressure on the inhale. So this fluid system is a simple mechanism, costs about $300 to build, and it provides some of the essential mechanics of ventilation. So I'm hoping that I can collaborate and turn this into an open source project and find a way to improve the design and make it so that we can build a very cost-effective, easy to build, easy to fix, or easy to even improvise, lightweight solution to what has become a global challenge.